Hi students, so welcome to the first lecture of environmental engineering. So in this lecture series we are going to learn what is the water supply engineering, wastewater engineering and solid waste management and also air and noise pollution. These are the topics which we are going to cover in respect of GATE examination. So what is meant by this environmental engineering? So what is the necessity of learning this environmental engineering? Even if you go to post graduation or if you are doing PhDs also. So what is this subject means? So why the subject is needed? What is the actual sense of this subject? See here, environment, we civil engineers always use or destruct the environment in order to having some kind of development activities such as building of roads, building of reservoirs or building of huge mega residential projects. So all these things, wherever you go, so you are disturbing the ecology there. Okay, so we need to understand the ecology over there. So how we have destructed, in the same manner we need to construct it in order to rebuild the existing equilibrium there which we have already disturbed it. So that is why a civil engineer has to do an environmental impact assessment of any project, and how can we rebuild the impact. That means if you are constructing a reservoir, you need to cut off many trees, forest lands, and if wherever you are doing deforestation, in the same manner you have to choose a location so to do afforestation also. This is also included in the project. So that is why, and also the biodiversity there also will get disturbed. So all these aspects needs to be taken into consideration. So this is a broader view of environmental engineering, but up to graduation level we only think a small bit of it. So that is simply we confine ourselves to the human needs. So day to day human needs, whatever the needs are there. So we have only confined ourselves in the graduation so to only the human needs, such as water supply to the communities, and whatever the water which is consumed by the communities are being collected back, and how to treat it safely, how can we dispose that wastewater into the environment again, so in order to safeguard the environment from the waste. Okay, so because we are deriving water, we are getting water from the environment only, so again we are sending the wastewater into the environment, so where you are getting back. So that is why you need to safeguard yourself without from getting the environment polluted by the wastewater which is sending. Our waste may be in terms of water, it may be in terms of solid, it may be in terms of gas, so it may be in terms of sound, whatever it may be, all are the pollutants. So how to safeguard the environment from all these pollutants, so all those things we will learn in this topic of environmental engineering. So this topic is broadly classified into water supply engineering. It is classified into water supply engineering, and wastewater engineering, and solid waste management, and air and noise pollution. So these are the topics we are going to cover in our environmental engineering subject. So let us start with the water supply. Let us start with the water supply engineering. So what is meant by water supply? Where it starts, where it ends. What are the various components of this water supply engineering, and how to design those components, what is the criteria of design, all those things we are going to learn in this subject. So water supply engineering. So water supply engineering, see, it is a supply, it's a supply. We are giving water. So if you are giving water, then you need to have the water first. If you are giving water, then you need to have the water. Where the water will present? So water may be present in oceans, seas or rivers, lakes. So But though the water is present in oceans and sea, but that water purification and make it fit for drinking is a costly affair and not necessary for a country like India, because we are having a plenty of fresh water in the form of various rivers. So that is why we use river water to water supply. So the sources are the rivers. Okay, the sources are rivers. So our water supply engineering starts with a source. Our water supply will start with a source. So source may be any river. So again, this source, sometimes this source may have a lot of water, but that water availability will be keep on fluctuating. See, some rivers are perennial rivers, but many of the rivers in India are not perennial, they are non-perennial rivers. So if the source is fluctuating, but the demand, user every day we need same amount of water for bathing, every day we need same amount of water for cooking. So people, the demand is from the people side, community side. So community side, there is no change in the water demand, even it is increasing day by day because the population is growing. Now, but the source is fluctuating. In the rainy season, the source will have plenty of water, whereas in the summer season, the source may have less amount of water. So there is a fluctuation in the sources. So that is why, so if the source is non-perennial, then we need to construct a project there in order to stabilize the demand. So in order to stabilize the water availability to meet the demands of the community. So that is why, so source fixing plays a very crucial role in water supply, because water supply completely dependent on this person, on this part. So okay, so without a proper source, your complete chain, supply chain will get disturbed. Okay, that is why, so finalizing source is a very crucial thing. Once the source is finalized, then rest of the thing can be done very easily. It is just financial. So here these are all man-made, but this is God-given, natural. Okay, so this thing needs to be finalized very carefully. Otherwise, what happens? The rest of the system, which is man-made, will of no use. So now after this source, after the source, now you got some water. So first question arises in your mind is whether it is a good water or bad water. Okay, so source, you have found a source. The next question is, so whether is it fit for drinking or not fit for drinking. So obviously it is not fit for drinking these days, as I told you. So earlier in ancient period, the industrial activity or the agricultural activity is very limited, but these days these two are very happening in a huge manner. So that means whenever you are doing an agricultural activity, whenever you do an industrial activity, you will get an effluents. Okay, those effluents again where? So you have no place to dump them other than environment, isn't it? So the environment is having a lot of patience, so it will give you the fruit and you dump the dust into the environment. So now, so that is why, so the source earlier stages, in the early stages, maybe the source directly might be fit for drinking, but these days never we find a source which is fit for drinking directly. And even our immunity system is also not that much to withstand a small amount of impurities in the sources. So that is why obviously the source needs to be treated. Okay, so the source water is needed for treatment. Then what a treatment I need to give? If you go to a doctor, doctor will not give you a medicine directly by looking at your eyes. So he will make some protocols like doing some kind of blood test or x-ray whatever it may be. So without doing a test to water, how can we find what kind of impurities are present, what kind of treatment is needed? So now, so generally what we do is, after finding a source, we check the quality of the source. Okay, quality. So we check the quality of source. So once you found the defects, so while doing the quality check, you will find the defects. So for those defects, you will do treatment. Okay. See, For this treatment, actually for this treatment we need conveyance of water. So here source and treatment may not be at a location. So it may be at location or may not. So that is why generally the source to treatment we need to convey. So we need to convey the water from source to treatment. That is called conveyance. So quality is a kind of testing. It is not there in the supply chain. So in the supply chain from source to treatment I need to convey. This is a component. This is not a component. It is just a requirement. This is different. This is different. It needs a structure. It needs a structure. It needs a structure. It does not need a structure. So quality, it's a kind of testing apparatus are needed. So it is not a structure, rather it is a testing apparatus. Okay. So this is a different thing. So once conveyance is done, so there we do treatment of the water, whatever the quality problems are there in those areas, we will do proper treatment, and then after the treatment we will send it to storage or well as community. So community, see, or we will send it for storage. And meanwhile, so treatment, so there are again two types. One is conventional treatment, conventional, and another one is miscellaneous treatments. Another one is miscellaneous treatment. See, conventional treatment means the primary sedimentation tank or secondary sedimentation tank. Okay, so filtration or coagulation, filtration, disinfection. So these things are conventional, because for every kind of water we need these kind of treatments. So this primary sedimentation tank or secondary sedimentation tank, because it may be having a suspended solid or it may be having a colloidal solid. So every water may have colloidal or suspended solid, may have microorganisms in it. So that is, these conventional treatments will present for every kind of source, and also some more are there, I will discuss it later. Whereas if you see the miscellaneous treatment, for example, removal of hardness, so removal of hardness, and also removal of fluorine, so these things are miscellaneous. They don't present for all kinds of water. So they are area specific. Okay, they are regional specific, area specific waters only they need, but these kind of impurities are present everywhere. So that is why, so we need to provide conventional treatment as well as miscellaneous treatment whenever it is necessary, and then we will send the water to the community, So now this is what is a broader understanding of supply chain of the water supply engineering. So let us come to the first and foremost and prime important component of our water supply, that is source. So how to fix up a source? See, source can be finalized by taking the demand into consideration. For example, if you are feeling thirsty, you'll go to a shop and you purchase a water bottle. Okay, now if you are feeling too much of thirsty, you will purchase a 1 liter water bottle. Or if you are going somewhere where you don't find any water, then you will purchase more water in order to cater the future needs also. Whenever you are going outside where you don't find proper water there, then what you will do, you will purchase one more bottle for you. So apply the same concept to a community. So whatever the concept, if now you are doing, so if you are feeling more thirsty, you will purchase a 1 liter bottle. If you are feeling less thirsty, you will purchase a half liter bottle. And if you are having your friend with you, then you will purchase one more bottle. And if you are going to a place where you don't find water, then you will purchase one more bottle for the safety of purpose for future needs also. So the same thing which we do in our real life also. See, whenever the community, so community means the public, okay, where you are sending this water, so their need may be fluctuating. It might not be the same, it may be fluctuating, but what is the need of those people, I need to cater those needs, isn't it? So here the source, fixing of a source, fixing of source can be done by three things you need to keep in your mind. By three things you need to keep in the mind. So here the first and foremost, who are taking the water? The population. Who are taking the water? Community means what? Population. So what is the population? So we need to first find what is the population. What is the population? And next is, see, this population should be at the end of the design life. At the end of design life. That means whenever we construct any structure, either it may be a reservoir, or it may be a treatment unit, or it may be a conveyance plant, or it may be a distribution system. So we construct different kinds of components. We construct various components to supply the water to a community, whatever be the component. Every component will have a design life. Every component will have a design life. In that design life, the source will have more design life than any other component, because source, I told you, it is in order to give a constant supply to the community, though the river or though the source is fluctuating, then we need to construct a reservoir there. So if you are constructing a reservoir, it is a big deal to acquire the land and all. So we cannot easily construct reservoirs like that. Okay. So that is why it is a very costly affair to to establish a source, and also it needs lot of human involvement, like you need to acquire land from many people, villages, you need to evacuate. All these things are very tough to do. That is why generally we keep a larger design life for sources especially, whereas rest of the design can be easily re-established. It does not affect much number of people than a reservoir or than building a source will do. So that is why the population, because this source has to feed the water till its death. Okay, that is what? Till the end of the design life. The source has to feed the water to the community till the end of the design life. So if it is working at the end of the design life also, that means at the end of the design life, what is the population we are having, for them also it has to give the water. That means, so that is we need to first forecast the future population, and what is the future population need, that much amount of water, whether it is present in the source or not, we need to first verify it. If it is not present, then what makes sense of investing crores of money in establishing a supply chain? So we cannot easily rebuild or replace this supply chain to another source. It is not a simple switch on and switch off. If you are constructing a full supply chain and then the source has got lost, somewhere source you found, then you need to shift the supply chain to the another source. Shifting is not that easy. This shifting is not that easy. That is why we need to first check whether the source is sufficient or not. This is called source sufficiency. Also we need to check. So source sufficiency can be checked by the population at the end of the design life, and also what is the rate of demand. Rate of demand. As I told you, if you are feeling thirsty, your rate of demand is 1 full bottle. If you are not feeling thirsty, your rate of demand is half bottle. If you are thinking of storage and your rate of demand is 2 liter, so you now understand this rate of demand, how much important if it is for a big population. For single person it is fluctuating from 50% to 150%, isn't it? So 1 bottle, half bottle and 2 bottle means how much variation, fluctuation you are having. So that is why the rate of demand also fluctuates like that. So that is why we need to establish a uniform rate of demand. Okay, so if you know the rate of demand, so rate of demand means single person's need. Rate of demand means single person's need. So if you multiply with the number of persons, you will get the community's demand. Community's demand for 1 day. So what is the community demand for 1 year? What is the community demand for the 10 years? So likewise you can get the total requirement of the water till the end of the design life. Okay, which helps us to understand the source sufficiency. And the third one is the design life. So we are doing all these exercise by taking design life into consideration. So what are the design lives of various components in the water supply system? Okay, these three things will decide the source sufficiency. Whether the source is sufficient or not, that thing will be understood by these three concepts. So now our next topic is knowing about these three. So if you know these three, then we can find whether the source is sufficient, whether the source is having sufficient amount of water or not. That we can identify only by knowing these three. So let us start with the population now. See, population, place to place it varies. So the growth of population in a city varies. Among the cities also it is different. If you look at Delhi, the population growth is different. If you look at Mumbai, the population growth is different. If you look at Chennai, it is different. So different cities will have different geographical conditions. So accordingly, different growth factors are there. So accordingly, the population growth will get affected. Now, population. See, population variation, the population variation can be known from a logistic graph. It can be known from a logistic graph which is drawn between population versus time. Time, population, this is PS, saturation population. This is PS. So the graph will be like this. This is called logistic graph. This is called logistic graph. Okay, logistic graph. So this logistic graph, there will be different points where the curvature is changing, so that those points needs to be understood clearly, because where the curvature is changing means it is entering into a new phase. Okay, so here for example, here the curvature is changing, here this curvature is changing, so here it is changing, so here it is changing. So I will make it into segments of different curvatures, uniform. So here it is a uniform curvature, here it is a uniform, here it is uniform, here it is another uniform curvature. Let us name them as A, B, C, D and E. See, AB, so the curvature is very less, small, gentle curvature. Okay, so here it is early growth. We call this as early growth. And BC is exponential growth. growth. CD, if you look at the graph, it is completely straight, vertical. So that is why we call this as constant growth. Constant growth. And DE is late growth or delayed growth. Late growth or delayed growth. So these are the different growth rates. So any city if you take, it may fall in any kind of these growth rates. It may fall in any kind of these growth rate. Either if it is a young city, very new city, then it will come into early growth. And if it is rapidly growing, then it comes into exponential growth. And if the city is already established, well grown, then we will be having a constant growth there. And if the city is too old, that means very old cities, there, so the growth, it cannot have the possibility of growing there. It is already completely grown. Then what happens? The growth will go on decreasing, and finally it meets the saturation point. When it is meeting the saturation, then the growth possibility is not there. Already the too much of the space is being completely exploited there. No space is available there. So very limited space is there. There the growth will happen. So that is why generally in very old cities you will be observing late growth or delayed growth. In emerging cities, exponential growth, already emerged but not too old, there constant growth. So yet to grow, there you will find the early growth, because we design this water supply majorly for the cities and towns. So that is why they will either fall in any one of the categories which I have mentioned here. So early growth, it's not a big problem, so we can easily control water over there. And delayed growth also, already system is completely existing there, so there also it is not a big deal for us to cater the needs. But whereas these two, so exponential and constant growth growing cities, so where majority of the cities are coming, so here I need to look at, because here I need to carefully design the water supply system. So let us go to the first one, that is constant growth. I will pick constant growth first, and then we will discuss about the exponential growth. So constant growth, if you look here, so here let us take, this is P1 and this is P2. Okay, this is P1, this is P2. So if you look at this, okay, if you look at this, dP, and what is this? Time difference. So there is a small time difference here. So there is a small difference here. So dP by dt. Okay, dP by dt. dP by dt. So any population you take, so this dP by dt will be constant here. So in constant growth, so the rate, constant growth means what? The rate of change in population will be constant. Constant growth means the slope. Here the slope is constant. For this graph, the slope is constant. That means dP by dt is constant. dP by dt is constant. Okay. So now if dP by dt is constant, okay, so constant growth, so if dP by dt is constant, then dP is equal to dt, let us take this as k. Okay, k into dt. So P1, I will integrate it between two populations, P1, P2 and T1 and T2. T1, T2. Now, this is nothing but dP's integration is P and the limits are p1 p2 and k into dt's integration is t and the limits are t1 t2. Okay, and the limits are t1 t2. Now so p2 minus p1, here substitute the p2 and p1 values. So p2 minus p1 is equal to k into t2 minus t1. So p2 is equal to p1 plus k into delta t. So p2 is equal to p1 plus k into delta t. So this is what is the formula we have derived from the constant growth. So let us discuss in detail about this. Let us discuss in detail about this. So dp by dt is equal to k, dp is equal to k into dt. So integrating it from p1 to p2, t1, t2, it is equal to p2 minus p1 is equal to k into t2 minus t1. Okay, so p2 is equal to p1 plus k into delta t. Now for example, we are having the population data like this. We are having the population data like this. So 1990, let us have the population of P1, and 2000, because we will be having the population for every 10 years, because we will be having the census data for every 10 years. So that is why we will be having the data of population for every 10 years. So it is P2, 2010 it is P3, and 2020 it is P4. Okay, I want the population in 2050. I want the population in 2050. Okay, so now here, K, what is K? K is nothing but dp by dt. K is nothing but what? dp by dt. So dp by dt means, dp means what? So here it is p2 minus p1. So what is dt here? dt is 1 decade, isn't it? It is 1 decade. So 1 decade. Similarly here, if you take p3 minus p2 by 1 decade, if you take here, it is p4 minus p3 by 1 decade. So we take this as x1, we take this as x2, we take this as x3. So then we will take the average of this. So there are different dp by dt values. For this, this is dp by dt. For this, this is dp by dt. For this, this is dp by dt. To have a uniform dp by dt, what I will do? I will take the average of all the readings which I got. Okay, and so on by the number of readings. Okay, so x bar is nothing but how many values are there by the number of values, then you will get x bar. X bar is nothing but average of k. So this is k, k1, k2, k3, or x1, x2, x3. Then x bar is the average value. Now here this x bar is per decade. It is not per year, it is per decade, because everywhere I am dividing it with decade. So now, so here, what is delta T then? Delta T also should be in decade, because the unit of this is population per decade. Here it is population. So the x1 unit is what? Population per decade. Okay, population per decade. This is decade. So here, if the unit of this is population per decade, then delta T unit should be also in decades only. In decades only. Then only decade and decade will get cancelled. You will get the population. Okay. So Pn is equal to, so I am writing now a uniform formula. So here I have taken between two values, but if I put P2 as a Pn, P2 as Pn, okay, then P1 will become P0. So this K will become X bar and delta T will become N. So this Pn is population after n decades. Population after n decades. Pn is population after n decades. P0 is latest known population. Latest known population. So here in this case it is 2020. Latest known population is 2020. And Pn is population after n decades. N decades means 2020 to 2030, 2040 and 2050. Here there are 3 decades. So here we are having 3 decades. So latest known population is 2020. We want population in 2050, means the difference is 3 decades. X bar is average growth. Average growth, and n is number of decades. N is number of decades. So if you are finding a city where the growth is constant, then we can find the population after n decades using this formula. And this formula, if you see, this formula is representing a arithmetic nth number of arithmetic progression. This is the formula of nth number of arithmetic progression. That is why we call this method as arithmetic increase method. Okay, we also call this method as arithmetic increase method. Arithmetic increase method. Arithmetic increase method. Okay, so this is arithmetic increase method, which we apply this method for old cities, where the growth rate is where the growth rate is constant. Where the growth rate is constant. So in those locations only we are going to use this arithmetic increase method. Okay. So next method is geometrical increase method. So we will discuss this geometrical increase method in the next session. Okay, for now, so this is what we have discussed. So we have discussed about the introduction part of the water supply engineering, and in that, so to find the source sufficiency, we need to determine the population. So for knowing the population for various conditions, criteria, so one of the criteria we have discussed that is arithmetic increase method. In the coming lecture we are going to discuss geometric increase method, incremental increase method, comparative graph method, simple graph method, all those things to forecast the population. So that we will discuss in the next session. Thank you so much.